Hi everybody. So today we are going to begin section 7.2 and we're going to talk about beams that are loaded in such a way that shearing forces will result in the beams. Now this section and the previous section 7.1 will build directly into material that you'll need when you take mechanics of materials, which here the number is ES 2410. So when you start to see this material, keep in mind that you will be able to use this in the future in another course. And it actually, part of the course will be a repeat. So this is a really a good amount of material to have, and it'll serve you well as we go forward. All right, so if we take a look at the PC, you'll see that today I'm going to be recording lecture number 28, which will cover 7.2. And then the last section that we will cover in chapter 7 will be 7.3. Then we'll do a few lectures after Thanksgiving on friction, chapter 8, and that'll be it for the semester. So we're definitely getting into the home stretch at this point. All right, so let's come over here to the document cam and we'll lay out some ideas about beams. So the first thing about a beam is that a beam is a structure that is meant to bear some sort of a load and is supported in different ways in order to do so. So the way that they draw a beam often looks like this, where this is a designation for a fixed support, meaning that it can bear a force in the y direction and a force in the x direction, and this is a rolling support. So what that means is, if you think about it being on rollers, if the beam is loaded, in some case, whatever you're doing to it, a support like this, a rolling support, can only bear a force in the y direction. In other words, if you push down on it, it's going to respond by pushing up. But in the x direction, it's going to not bear a load at all. It's just going to move a little bit. And this is actually something that happens with bridges. If you look at any sort of a bridge, as you load them, they will expand or contract, depending on if they take on a significant U shape as they're loaded. And also, as they get hotter and colder, they'll expand or contract. So bridges will have expansion joints or rolling supports in order to prevent them from buckling and damaging the structure. So even though this is a simplified version, it is definitely a real sort of a situation. So this type of a beam is referred to as a simply supported beam, and there are other types of beams or other types of support. One, if the rolling support, for example, is not at the end but is somewhere other, this type of a support system would be called an overhang beam. A beam that's extruded from a wall, like a signpost, is just supported on this end, is called a cantilever beam. And then there are some other types as well. But basically, when we go to analyze any type of a beam, we do the same sort of a thing, where the summation of forces in the y direction, summation of forces in the x direction, and the summation of moments about any point on this beam have to be equal to 0, or else the beam is going to move. So when we start talking about beams, we've talked previously about what are called point loads. Specifically, we haven't really even called them point loads, we've just called them loads. So if you push down on the beam at some point, you can just think of a force P acting on that beam. But sometimes there will be a distributed load. In other words, instead of having a load in, say, pounds or newtons, you would have a load that's distributed in terms of maybe pounds per feet or newtons per meter. and that is generally designated by the letter W. Now, the total load that you get from something like this, if it's flat, if it's consistent, the total load is equal to the load per foot times the distance over which that load per foot is applied. And this, you can think of it in some cases as acting at the center, at the centroid of the load curve. So if the load curve is a rectangle, it's going to be smack in the center of that load curve. Now, there are other types of loading. For example, you may not have a consistent load like this. You may instead have a load that looks something like this, where you have, maybe it starts at 0 and it goes up to some value which we might call W sub 0, and the load curve itself is a triangle. In other words, the load becomes stronger or heavier as we go from one side to the other. In this type of a case, the area under the load curve equals that load, and so the area under this load curve, what shape is that? If you just think about this line, and this line, what is that shape? Triangle. Yep. And so the area of a triangle is 1/2 times the base times the height of that rectangle. And from our discussion of centroids, we can say that that force W, the equivalent force, acts at the centroid of that triangle, which is 1/3 of the way from the base. Okay? So in other words, we can analyze that geometrically. Now there are other odd types of load curves in different shapes, but we're not going to have those in this course. You may see some different shapes of load curves in mechanics of materials, but this is a great starter. This is a great start. So why are we interested in this? Well, the answer is, when we were talking about chapter 6, we talked about 2 force members, and that meant that the structural member was either in tension or compression or neutral. The force was directed along this axis of the structural member. This would be tension. It might be the other way, which would be compression. But here we have a different type of a force situation. If something is in tension, compression, neutral, and the load is directed along the axis, we refer to this as a normal force. It's normal, not meaning as opposed to abnormal, but as opposed to perpendicular. Normal, or it meaning perpendicular to the cross section. Okay, so the direction of the load with respect to the structural member is what makes it normal, because it's perpendicular to cross section. Well, if we have a situation like this, the load is not going to be perpendicular to that cross section, but it's going to be parallel to the cross section. And we refer to that not as a normal load, but as a shear load or shearing load. Right? So shear tends to create a shear plane where an object will try to pull against itself in this direction, whereas normal or a normal force tends to pull it apart or push it together. Now, the first idea that we need to take a look at when we discuss this is a sign convention, because we know that for a normal load, for a normal force, that tension is positive, compression is negative. And those are two kind of physically different things. The direction is the same, it's still perpendicular to a face of that curve, but they mean kind of different things. For a shearing load or a shear load, a shear force, The sign convention is just based upon a direction of rotation. And you're saying, huh, what does that mean? Well, what it means is that if we have a structural member and we cut it, which I'll explain in just a moment, we want to look at what's going on here. The shear load here is going to be equal and opposite to the shear load here. In other words, it's just a tendency for those two surfaces to pull against each other. And so the sign of whether it's positive or negative is really a convention. Okay? So for a shearing force, you can do either way. You can start on the left and cut on the right. Just start on left, cut right. V down is positive. Okay? Because it's exactly the same, just looking at it from a different angle, if you start on the right, cut on the left, this up is positive. All right? So what that means is that it doesn't have the same sort of meaning as tension and compression. It has a little bit different. And if you do it wrong every single time, you'll still come out with the right answer. But this is just the standard way of doing it. The problem is that if you do it however you feel like it, if you do it one way one time and one way the next time, you'll confuse your work. So I recommend strongly that you always use this sign convention, which is also what the authors use. And it is pretty standard. Okay, so what that means is, let's look at a beam. All right, if we have some sort of a support over here, reaction forces, reaction, I'll call it point A in the y direction, and reaction point A in the x direction. And we cut our beam and look at it right here. This is a positive normal force, which is generally designated as P. This is a positive shearing force, which is generally designated as V. And this is a positive moment, which is generally designated as M. Okay? And in this way it makes sense, because if you look at it, that's a counterclockwise rotation, which has always been positive for a moment. Now if you cut on the other side, the exact opposite directions should be positive. So in other words, if you cut the other way, here's my, I'll call it RBY and RBX. This is positive P. This is positive V. And this is positive M. All right? And we could, just to separate those, we could just call those primes. All right, so today what we're going to talk about is what that shear looks like across a beam. And we're going to draw something called a shear diagram. Now, the reason that we draw shear diagrams is because normal stress tends to distribute itself, or normal forces tend to distribute themselves pretty uniformly. Shearing stresses concentrate at different places, and that's why like fasteners and bolts and nuts become such a big deal. They tend to be subjected to very high amounts of shearing stress, and they have to be very, very strong. So we're going to learn a technique for taking a beam and understanding what the shear is from one side to another. We can do the same thing with bending moments, which we will talk about. I don't think we're going to get to it today. I think we're going to talk about it on Friday. Okay? So today we're just going to talk about a shear diagram. So I'll give you a couple of homework problems that will say do a shear diagram and a moment diagram, but you don't have to do the moment diagram until we cover that material on Friday. All right? All right. So let me draw problem 7.29 in your textbook, and then I will I think I'm going to start with 7.31, just because it's very straightforward, and then I'll do 7.29 after. Okay, so 7.31 looks like this. We have a rigid support at point A. We have a rolling support at point C. And here at point B, we have a load P. The distance from A to here is 1/3 of the beam's length. And so from here to here is going to be 2/3 of the beam's length. All right. And the question 731 says, draw the shear and bending moment diagram. So we'll just do the shear diagram. And then it asks me to determine the maximum absolute value. Okay, so it's going to ask me for the maximum absolute value. The reason we want maximum absolute value is, once again, because the sign doesn't make a difference in terms of, it's just a direction, it's a directional thing. So you want maximum absolute value because that's where the most shear is going to be concentrated. All right, so let's go ahead and draw a free body diagram. A is a fixed support, meaning that it will bear both an RAY and an RAX. And then we have load P, and over here at C, we have RCY. All right, now the first thing that you notice is, if we do a summation of forces in the x direction, we know they have to equal 0. That means that RAX has to equal 0. There's nothing to oppose it. There's no applied loads, no reactive loads in the x direction. So this is equal to 0. So the next thing we can do then is to say summation forces y equals 0. And here we have 3 loads. We have reaction RAY, we have reaction RCY, and we have the load, applied point load P acting down. Those 3 things equal 0. So we know that, in other words, RAY plus RCY is equal to P, but we can't tell how much of it is borne over here and over here. If this were smack in the center, we could probably make an assumption that it was borne equally. But since it's not, we're going to have to sum moments about a point in order to find out what that load is. All right, so let's say the summation of moments about point A. Those have to equal 0 as well. That will eliminate RAY. So we have the force of P, and the moment arm there is L over 3. And if I pretend like I put a pin here and I rotate, that's clockwise. So it's negative. We then have RCY times its distance from point A, which is L. Put a pin, push up on that force, it's counterclockwise, so it's positive, and that is equal to 0. So that means I can solve for RCY. It's going to equal PL over 3 divided by L. So those cancel out, and we get that RCY is equal to P over 3, or 1/3 P. So if this is 1/3 P and this plus this equals P, this must equal 2/3 P. Okay, so far we're sort of on familiar territory. Yes. Oh, sure.
Does the negative, because you had it as negative P to the L divided by underneath.
Here?
No, sorry.
Over here.
Like you had started the equation, it's like that one.
Okay.
The negative in front,
Yes.
does that go away?
Well,
Because
it comes
it's
over to the.
absolute value?
It's great. Not yet. No.
Okay.
But it comes over to the other side as a positive.
As a positive.
Yeah.
Okay.
Good, excellent question. Thank you for that
Sorry.
clarification. No, I'm glad you asked, because sometimes I just get like into it and I forget to explain
No, I
like
should.
the basic, most important things. So,
Well,
no, that is the correct answer. Yeah. So it's just this is negative because if I pretend like I hold it here at that point A that I'm taking the moments about, and if I think about what kind of a rotation P would cause, it would be clockwise, which is negative. But then it becomes positive. Yep, on the other side. Excellent point of clarification. All right, so now I know it asked me to draw a shear diagram, and this is where we are doing something new. So the first thing we do is we draw our free body diagram that looks like this. We have RAY, and we have a value for that, 2/3 P. And then we have P, and then we have our CY, which equals 1/3 P. All right, shear diagram, V. The first thing that we do in terms of our technique is we draw right underneath our free body diagram a diagram that's going to show what my shear force looks like at every single point along this beam. And the way that we do it is, we talked about cutting the beam. So every time that there's a change in the loading situation, I cut there. So in other words, from here, from 0, x equals 0, to x equals 1/3 times L, which is where P is applied, everything's going to look the same. There's no change in the loading situation between those two things, right? So my first cut I'm going to make, it's my cut, prior to from 0 to 1/3 L. Okay? So if I cut there, then I would say this is my positive V. I know this is my positive M. I'm not going to work with that today, but I know that that's also true. Okay? And then if we had a P, it would look like, if we had a normal force, it would look like that. All right, so in terms of V, if I look from here to here, I can say summation forces Y equals 0. This is positive, 2/3 P. And now I've drawn it like this, but in this diagram that becomes negative because it's down in a free body diagram. So that's equal to 0. So that means that 2/3 P is equal to V. So that means from, this is another point of the diagram, we can just draw a line like this, from the very beginning to the point where P is applied, V is equal to 2/3 P. That's the first part of my diagram. Now something changes from here to here, and that is, this is from 1/3 L to L, from here to here. Okay? I have a 2/3 P force acting here. Then I have P acting here. And then I cut before I get to the end, draw my V, and like I said, I draw my moment, which we'll work with next time. So all we're working with is the V. So then I say summation forces Y equals 0. I have a positive 2/3 P minus P minus V equals 0. 2/3 P minus P is negative 1/3 P. Negative V comes over to the other side as a positive V. And so what I find is that right here, from here to the end of the beam, my V value is negative 1/3 P. Now there's 2 points I'm going to make here, and I'm going to show you a little bit more. This discontinuity, where P is applied, in other words, where it shifts from being a positive shear to a negative shear, is the way that shear works. You have these discontinuities, and that's really where things are going to fail. Now it also asks, where is the maximum shear? Well, it's everywhere here, isn't it? This is the maximum shear. Now, this is negative, but if the absolute value had been higher, this would be the negative. I mean, it would be the max. So all we're looking for is that maximum value. What does it mean that it was negative 1/3 here? Well, look, if we cut from the other side, if we made this choice and we looked over here at our CY instead, We know that the value of RCY is 1/3 P. And if we did that up until the point where we cut from P, which is right here, so we cut right here. When we're cutting from the right to the left, we would draw our V looking like this. So then when we did the summation forces Y equals 0, we would get V plus 1/3 P equals 0. Solving for V, we would get V is equal to negative 1/3 P. That's exactly what we got here, which is kind of the whole idea. That if you cut from the right or you cut from the left, you're going to get the same results on a shear moment diagram. So what this does is it organizes the shear, shows you where it's going to be the maximum, shows you where you're going to have discontinuities, and then, like I said, it also shows you that you can work from one side or the other. I tend to work from the left to the right when I do these types of problems, but if there's a whole bunch of complicated stuff over here, I'll definitely start from the right and cut on the left. Absolutely. Right. Let's look at one other one. I'll do 729 so that we can take a look at what's going on with a distributed load. Okay, here on 729, we have a beam that looks like this. Here's point A. Here's point D on rollers. And the entire length of the beam is L, but a quarter of the way in, quarter of the way in, and a quarter of the way from this end, we have a distributed load, which is W. All right, so if this is a quarter and this is a quarter, that means that what's left here is going to be a half times L, right? So in other words, my capital W is going to be the W times X, which is W times L over 2, or little w L over 2, meaning that's going to be the equivalent point load. And because this is a rectangle, we can think of it as being applied right here. Now, that is for the purpose of doing moments. When we do shear diagrams, we're going to have to distribute it because obviously the shear is going to be different 1 foot in than it is 2 feet in because we're increasing that load. So that's what I'll show you next. All right, so the first thing we want to do, free body diagram. We want to determine what is the reaction at A, what is the reaction at D. Well, we can do moments, but since this is symmetrical, we can also see that half the load is going to be borne here and half the load is going to be borne here, right? So if the total load is WL over 2, the reaction at A in the Y direction is going to be WL over 4, and the reaction at D in the Y direction is also going to be WL over 4, right? So we need to do a cut here, and we need to do a cut here, so we need to look at the straight line portions here and here, and then what's going on underneath that load curve in terms of our shear. So here's my shear. Let's look at this. From 0 to L over 4, from here to here, we have a single load of WL over 4 acting up. And when we cut and we put V like this, that's all we have from here to here. So that means we have WL, the summation force is YWL over 4 minus V equals 0. WL over 4 equals V. So that means from here to here, this is positive, and its value is going to be WL over 4. Okay, now on this side, if I were to cut the other way, I know that my RDY is also WL over 4. And so if I go from L, or from actually 3/4 L to L, I would draw, since I'm cutting on the other side, my V would look like this, draw it up. And so here I get, this is positive, WL over 4, and here I have plus V equals 0. which tells me that V is equal to negative WL over 4. So that means from here to here, the end of the beam, this is going to be negative WL over 4. What happens from here to here, that's the new part. All right, so let's draw a cut right just arbitrarily into that load curve. Okay, so I'm going to start on the left with my reactive load, WL over 4. Then I go some distance. And then here, I'm going to have this, which is W. If I call this L over 4 plus X, in other words, however far I am into the load curve, whether it's 1 unit, 2 units, whatever, I could say that my W at that point would be equal to W times X, right? So wherever I am, I'm going to have that load immediately to the left of WX. So if I do a summation forces Y equals 0, and draw my V down like that, I get WL over 4. And this is up, this is down, minus W times X, starting here and going all the way across that load curve, minus V is equal to 0. So what I find then is that WL over 4 minus WX is equal to V. All right, what that means is starting here where my X is 0 and going to here where my X, let's do that, where X is L over 2. Where X is 0, my V is going to be WL over 4. So that tells me that my starting point is here. But what about here? My X at that point is L over 2. So at X is equal to L over 2, I get my load WL over 4 minus W times L over 2 is equal to V. So WL over 2 minus WL over 2 is equal to V. I've got a sign wrong here. Oh, this is 4. This is WL over 4. There we go. Sorry about that. I drew it right here, but I drew it wrong here. So I have W at the end of that load curve. Then I have WL over 2, get a common denominator. So I get WL minus 2WL over 4. I'm going to have to write that out. I'm sorry, this is messy. So I get WL over 4 minus 2WL over 4 equals V. And if I look at this, 1 WL over 4 minus 2 WL over 4 is negative WL over 4 is equal to V. So that means that here it's exactly equal to that point. And I can see that since it's a function of x, not x squared, it's going to be a straight line. So my load curve looks like this. My V curve, not my load curve, but my shear curve looks like this. So what that says is on the left-hand side, I have a consistent shear until I get under the distributed load curve, at which time the load decreases, and right in the middle of the beam, the load's going to be equal to 0. The shear is going to be equal to 0. It decreases to the load on the support on the right-hand side. And so I can see everything about this curve. I can see where my maximum shear is. I can see where my 0 shear is. And I can see how it changes across the length of the beam. Right. So do you guys have any questions about that? It's a lot and takes a while. So what I'm going to do is I will just assign you 2 problems. We're not going to do a triangular problem, a triangular load curve. I'll do a point load problem and a distributed load problem with numbers instead of letters. And I'll post those to our page. excuse me. I'll post those to our page as soon as they process this video for me. And then when we come back on Friday, we will continue our discussion. Now, on Friday, do check your email. I know that you know most people don't come on Fridays, but I may not be here. We're going to go up to MSU Billings. Yes, so we're looking at some partnerships with them. And so we're going to go visit them, and I'm not sure when I have to leave because I'm going with other people from the college, so they'll tell me when I have to leave. So if I have to leave before this time, I will send you an email and let you know. All right? All right, thanks, guys. Have a wonderful day, and we'll see you maybe Friday.